Hello, fellow seekers. This marks the continuation of my video on our nearest stellar neighbors. I don't see it as a second video in a series, rather as the second part of a longer video. If you have any questions regarding the map, how it works, the directions I'm using, or the names Luyten, Gliese, Ross, or Wolf, I recommend watching the previous video, link right there. Just a note, I made a few errors in my previous video. I described the Lumen 16 binary as 34 and 29 Earth masses when obviously I meant Jupiter masses. Also, I listed Deneb as one of the 4 closest A-type stars to the Sun when I should have said Altair. I have no idea how that happened. When I last left off, we had just paid a visit to the decidedly unremarkable star Gliese 1028. West of Gliese, and fully 17 parsecs north, essentially bouncing from one end of the sphere to the other, we find the first star in my pinball sequence with a proper name. I must admit, when I first saw the name Chara on the map, I assumed it had to be one of those newfangled names the IAU awarded after polling the general public in the 2010s. But while it isn't of classical provenance, Chara, or more accurately, Chara, is a name with a fairly deep history, if a slightly comical one. The names of the stars are the West's last great fossil of the Islamic Golden Age, most of whose contributions have been overwritten by the works of Europeans like Galileo or Roger Bacon, both of whom often relied on Islamic sources. One of the drawbacks of doing so was having to translate Arabic, not exactly a lingua franca in post-medieval Europe. Still, the game of telebones worked both ways. When first translating Ptolemy's Almagest into Arabic, the scholar, and apologies in advance to any native Arabic speakers in my audience, Hunayn ibn Ishaq, when listing the stars of the ancient constellation of Boötes, the ox herd, translated the Greek koloboros, club, as kulap, meaning a hooked staff. Upon receiving the Arabic translation, Gerard of Cremona, the 12th century Italian monk whose translations are one of the less appreciated triggers of the Renaissance, read kulap as kilap, meaning dogs. So for centuries, a tale circulated around Europe that the ox herd was accompanied by his favorite dogs. And then along came Johannes Hevelius, brewer, politician, moon mapper, and, like Nicolas Lacaille a century later, inventor of lame constellations, including my least favorite of all, Scutum. Hevelius' actual name appears to have been somewhat fluid, but was likely Johann Hevelka. Born in the Kingdom of Poland in 1611 to German-speaking parents, he is most famous today for his map of the moon, which I am sure was an inspiration for the artists of Final Fantasy IV. While most of his names for the moon's features have since been overwritten by the more poetic creations of Giovanni Riccioli, he is the reason the moon, like Australia and Transylvania, has Alps. Hevelius' lasting legacy, sadly, was in creating new constellations, of which he crafted 10, 7 still extant. Given to seeing constellations where none had been before, in 1687, Hevelius decided that not only should the ox herd have dogs, but that those dogs should have names. And so, the tiny constellation of Canes Venatici, the hunting dogs, was born. Keep in mind, this was now the 3rd constellation named after dogs, including the one with the dog star in it. For the northern dog, Hevelius chose the name Asterion, meaning little star, thus naming a star after a dog named Star. For the southern dog, he chose Chara, a Greek word meaning joy, which Richard Hinckley Allen, in his book Star Names, Their Lore and Meaning, says was intended to mean dear to the heart of his master. So, with Boötes the ox herd now saddled with dogs he never wanted, just how good a dog is our little Joy? Well, by our standards, pretty spectacular. Just 3% more massive than the Sun, with a 12% greater radius and 15% greater luminosity, it couldn't be more Sun-like if it were auditioning. Even its metallicity is close, suggesting it is similar to the Sun in age, if slightly older. While no planets have been found around it as of yet, astrobiologists are drooling to see what secrets it might hold. with some declaring Chara to be the top candidate within 10 parsecs to host extrasolar life. Good boy. Just west of Chara, and dropping 11 parsecs back south, we reach Van Maanen's star. Born in Sneek, in the Netherlands in 1884, Adriaan van Maanen, like every Dutch astronomer of note in the previous century, fell under the influence of Jacobus Kapteyn, who nudged him toward the Mount Wilson Observatory in California, where van Maanen would work until the day he died, in 1946. Throughout his working life, van Maanen's obsession was tracking faint stars, and by faint, I mean of 15th magnitude, or 10,000 times dimmer than the star Vega. Given that many objects of that magnitude, such as Chiron or Charon, weren't found until the 70s, to tackle such levels at the turn of the 20th century was a cyclopean task, and van Maanen was very good at it. Of the 30 stars of 15th magnitude known when he died, van Maanen had found 15. One star, located in 1917, was of particular interest to another Dutch immigrant, Willem Luyten, who in 1923 christened it van Maanen's star. The reason van Maanen's star so fascinated Luyten is that it was the most striking example of a new class of stars that Luyten had called white dwarfs. Tiny, dense, and incredibly dim, these strange outliers were hot and white, while all dim stars found at that point had been cold and red. While van Maanen's star was not the first white dwarf to be found, it was the first known solitary example. The others, Sirius B and 40 Eridani b, orbited other stars. By the 1920s, it was realized that these were the exhausted corpses of ancient stars, reduced to ultra-dense husks held up by the laws of quantum mechanics. Van Maanen's star is close to being the type specimen for its species. It has a mass roughly 2/3 that of the Sun, but only 1% its radius. Its outer atmospheric temperature is 6,000 K, which, while hotter than the Sun, is relatively cool for a white dwarf. This suggests that van Maanen has been radiating its residual heat for some time, and maybe as much as 3 billion years old. Its child form, which is estimated to have lived for just 900 million years before expanding to about the size of the supergiant Betelgeuse, would have appeared in the skies of an Earth just seeing the first wisps of oxygen in its atmosphere. Van Maanen shows evidence of heavy elements in its atmosphere. As it should have swallowed such material over time, that suggests the material may be constantly replenished, such as by an orbiting ring of falling debris. West of van Maanen's star, and in line with the Sun, we come to Ross 248. Not to be confused with the far more interesting Ross 128, Ross 248 is a near twin of Proxima Centauri, with its near-exact mass, radius, and luminosity. It shows evidence for a solar cycle of 4.2 years, and was actually the first star to have its variability attributed to star spots on its surface, making it a BY Draconis variable. So shouldn't they be called Ross 248 variables? The only truly interesting thing about Ross 248 is where it's going. In about 80,000 years, it will briefly come just shy of 3 light-years of Earth, becoming our closest star. Slightly rimward and 1 parsec south of Ross 248, we come to Groombridge 34. I feel I owe an apology to the dedicated and perseverant 19th century astronomer Stephen Groombridge. In my video on names I wanted changed, I may have oversold the difficulty in pronouncing his consonant-laden name. I also failed to consider how those hard consonant clusters would appeal to authors of military science fiction, like Above and Beyond, Elite, and Halo. I also want to reiterate that I have nothing but respect for the man who spent 10 years compiling his catalogue of circumpolar stars, despite such inconveniences as a paralyzing stroke and death. The work was published posthumously. And while it suffers from the same issues as all red dwarfs as regards habitability, I must say Groombridge 34 is looking like a fairly decent outpost for humanity. It's a binary of 2 red dwarfs, both flare stars, one about 40% the mass of the Sun, the other slightly larger than Proxima. The two stars orbit each other at a distance of about 150 AU, completing one orbit every 2,600 years. And yes, that distance is wide enough for planets. And in 2014, 2 planets were found around the larger star. One a super-Earth of 3 Earth masses that orbits its star every 11 days, another a super-Neptune of 36 Earth masses with an orbital period of about 21 years. That's a gap just begging to be filled with a planet, assuming it can deal with the flares and the meager sunlight. Just coreward of Groombridge 34 and 9 parsecs north, we come to Gliese 508. The only interesting fact about which I can find is that it seems no one can agree if it is a double or triple star. The map has it as a triple. Sinbad has it as a double. 3 parsecs south, we arrive at this brown dwarf, which is actually far more interesting than it looks. It is what is known as a Y-class brown dwarf, the coldest class of brown dwarf known. With a surface temperature of just 500 kelvins, or 226 degrees Celsius. Its atmosphere contains compounds, such as water, ammonia, methane, and hydrogen sulfide, that we usually associate with cold ice giants, like Uranus or Neptune. Another thing that makes it interesting is that it has been shown to be a periodic variable. No one is entirely sure what is causing the variability, but it may be anything from shifting clouds to atmospheric holes to hot spots. 9 parsecs south, we arrive at Gliese 908, a solitary red dwarf about 40% as large as the Sun, a bit feisty and flary, but with a surprisingly low metallicity, suggesting it is quite old. 3 parsecs north, we arrive at Struve 2398, a binary red dwarf system named for Friedrich Georg Wilhelm von Struve, in whose catalogue it lies. Astronomy owes a lot to Struve's. Over the course of 200 years, this distinguished Estonian-German family would produce an astonishing number of accomplished astronomers. Of the 17 Struves notable enough to have Wikipedia pages, 8 are astronomers, some of whom I have mentioned in other videos. Friedrich Georg was the first to take up that profession when he joined the Dorpat Observatory in 1813 after jumping out of a second-story window and fleeing Germany to avoid being press-ganged by Napoleon's army. Struve is best known for his work with binary stars. By 1840, he had precisely measured the orbits of 2,700 binaries, including this one. The pair are about 1/3 and 1/4 the size of the Sun, respectively, and orbit each other every 295 years. They have a wildly eccentric orbit around the galactic center, which gives them a high proper motion relative to other stars. This suggests that, like Barnard's star, they may have originated from outside the galaxy. Though unlike Barnard's star, evidence appears to suggest the pair are quite young, at just 3 billion years. In 2019, 2 Neptune-sized planets were tentatively detected around Struve at distances of 0.26 and 0.43 AU, though they have yet to be confirmed. Continuing coreward and in line with the Sun, we arrive at 61 Cygni. It's hard to overstate the importance of this nondescript double star, one I'm sure many of you have never heard of, but it has a justifiable claim to be the most important star in human history. There is a simple reason why. After Sirius, it is the closest star easily visible in the northern hemisphere, which makes it the closest star readily observable to the first cultures to use telescopes. Close stars and telescopes mean only one thing: parallax. There is a reason I chose parallax as my name. It is the one solid foundation upon which to build a conception of the universe. Everything else is built on top of it. In order to understand just how vital to our conception of the universe 61 Cygni is, you have to go back to the beginning. And I mean the beginning. As far as we know, human beings are the first animals to tell stories about the stars. Other animals, such as birds, seals, and even dung beetles, have been shown to use starlight for navigation. But whether they ask themselves what stars are or why they are there, we don't and will likely never know. But at some point, likely somewhere in northern Africa about 300,000 years ago, a distant ancestor of me and you looked up at the lights in the night sky and asked him or herself what they were. The answers his descendants conceived were as varied as humanity itself, but most envisioned a world in which Earth, the realm of life, sense, and solidity, lay below a higher realm of heaven, a realm of portents, gods, and eternal truths. This realm was both awesomely distant and comfortably close, a realm which humans could not touch, but from which gods could descend, and warnings and omens could be interpreted. The ancient Greeks, the first culture to scientifically study the stars, believed they had a naturalistic rationale for this worldview. The earth was heavy. Heavy things fall, and, as the heavens were obviously a sphere, the earth would fall to the bottom of the sphere, the center. The earth was also obviously motionless. If it spun, or moved of its own accord through the heavens, then the air would rush off the surface with the force of a hurricane. Objects thrown or dropped would be pulled in the opposite direction to Earth's motion. But most importantly, the Earth was as a point to the heavens. If it were not, then, as we moved across its surface, we would see the stars appear to shift position as we viewed them from different angles. That is parallax. If, gods forbid, the Earth moved, then surely as it cycled from one point in its orbit to the other, we would see parallax as well. The Greeks, limited to their eyes, could not see any such shifts, and thus concluded the Earth was motionless. To suggest the alternative, as some Greeks had, was to envision a universe in which not only the Earth, but its entire orbit, and thus the orbits of all the planets around it, was as a point to the heavens. A universe effectively infinite in size, a universe in which the Earth and its surrounding planets were lost and alone in a vast, black emptiness. What room for gods, signs, or portents then? It is often said that Copernicus proved the Earth moved around the sun. That is false. Copernicus merely suggested, as others had before him, a possible alternative vision of the heavens that he found, in his words, more perfect. The Ptolemaic geocentric model explained the motions of the planets as well as Copernicus's. In fact, Copernicus's was slightly clunkier. What Copernicus did was throw an idea into the ring at precisely the right time, because within 70 years of his publication, in 1608, the telescope was invented. 2 years later, Galileo was the first to throw a wrench into the Ptolemaic model when he showed that Venus orbited the Sun. In 1758, the calculated return of Halley's comet locked Newtonian mechanics, and its required heliocentrism, into the scientific consensus. No one of any scientific education could doubt the Earth was in motion around the Sun. And yet, despite telescopes increasing in power, parallax, the direct evidence of Earth's motion and the extent of the universe, remained unobserved. The search for parallaxes was not just about putting the final seal on heliocentrism. By measuring a star's parallax, you have a direct means to measure its distance from Earth. Parallax would allow astronomers for the first time to comprehend the true distances of the universe. James Bradley was searching for parallaxes when he discovered the aberration of starlight in 1729. William Herschel was searching for parallaxes when he discovered Uranus in 1781. But the honor of the first measured parallax would go not to a legend like Herschel, but to a one-time dropout in East Prussia named Friedrich Wilhelm Bessel. Born in Westphalia in 1784, Bessel left school at 14 for an apprenticeship, concluding that anything else he needed to know he could learn from books. He eventually left the apprenticeship too, after a course in astronavigation passed on the astronomy bug. Thankfully, he was a mathematical prodigy who, in 1804, deliberately accosted Heinrich Olbers, who had just discovered the asteroid Pallas, with his calculations for the orbit of Halley's comet. So impressed was Olbers that he immediately took Bessel under his wing, and helped him get his first job at the Lilienthal Observatory. He soon made a pen pal of Carl Friedrich Gauss, the mathematician and polymath for whom the unit of magnetic field strength is named. This contact got him an in with King Frederick William III of Prussia, who appointed him, aged 25, director of the Königsberg Observatory in what is now Kaliningrad. Bessel spent most of his time at the observatory fixing positions of 50,000 stars. But upon hearing of Wilhelm Struve's attempt to measure the parallax of the bright star Vega, he decided to take up the search himself. And he knew just which star he would use. In 1804, Giuseppe Piazzi, the astronomer and Catholic priest who discovered the asteroid Ceres, identified what he called his flying star, a star with a remarkably fast proper motion, physical motion through the cosmos, indicating that it had to be very close to Earth. It was also present in the sky for most of the year, and close to other stars that could act as a backdrop. Using a state-of-the-art micrometer, in 1838, after 25 years of attempts, Bessel measured the flying star's parallax. 61 Cygni, according to Bessel, was 10.3 light-years away, about 10% off its current value. But precision doesn't really matter. From that day, the distances between Earth and the heavens had finally been fixed. In the future, if anyone ever asks you who proved the Earth goes around the Sun, now you have your answer. Friedrich Wilhelm Bessel. Some today insist on referring to 61 Cygni as Bessel's star, while others prefer Piazzi's flying star. So, what is 61 Cygni like? Well, if I'm honest, it's punching severely below its weight. Ostensibly a distant binary of two inviting K-class orange dwarfs, the pair actually behave more like red dwarfs. The dominant partner, 61 Cygni A, has about 70% the Sun's mass and radius, but only 8% its luminosity, while B has about 2/3 the Sun's mass and radius, and just 4% its luminosity. Like many red dwarfs I've listed, A is a BY Draconis variable, so pocked with star spots that they can be seen across interstellar space, while B is listed as a flare star, often doubling in brightness. The two orbit a common center of gravity every 659 years, at an average distance of 84 AU and a minimum distance of 44 AU, wide enough to contain two decently sized solar systems. However, despite searches going back to the 1940s, beginning with, who else, Peter van de Kamp, no planets around either of 61 Cygni's two suns have yet been detected. Age estimates for the pair range from 2 to 10 billion years. Whether any potential planets could possibly host complex life has yet to be known with certainty. Next up, Gliese 1286. It's Proxima Centauri. Next up, Gliese 687. Another large red dwarf, with 40% the Sun's mass and roughly its metallicity, suggesting it is of similar age. It houses a Neptune-sized planet with an orbital period of 38 days, which might place it in the star's habitable zone, and another exo-Neptune with an orbital period of 727 days. A little rimward, we arrive at Kruger 60. If there is one lesson to be drawn from the life of Karl Nicholas Aldebrecht Kruger, it is that nepotism works. And yes, that is how you spell his name. There appears to have been some loss in transliteration. In 1853, while still a student at the University of Bonn, he became the assistant of Friedrich Wilhelm Argelander, a name we will be seeing again. With Argelander, he began work on what would, in 50 years, become the Bonner Durchmusterung, the catalogue of 325,000 stars that is still used today. In 1858, he began parallax measurements of several stars, including Groombridge 34. In 1862, he married Argelander's daughter, and in 1881 was given editorship of Astronomical News, arguably the first solely astronomical scientific journal. When he died, editorship passed to his former assistant turned son-in-law, Heinrich Kreutz, who would go on to discover the Kreutz Sungrazer comet family. So all was well. As for the system itself, well, it's yet another red dwarf binary. Each star is about twice the size of Proxima Centauri, and of course, one of them, B, is a flare star. The two come as close as 5.5 AU, and so are unlikely to possess large planetary systems. By far the most interesting thing about the system is a 2019 study by a group of Polish astronomers who have suggested that Kruger 60 may have been the point of origin for the interstellar comet 2I Borisov. A model of the comet's past motion through the galaxy produced Kruger 60 as the only likely candidate for its birthplace, though they also acknowledged that uncertainty in the radial velocities of the stars made their conclusion shaky at best. East of Kruger 60, we come to this brown dwarf, which, astoundingly, has a Wikipedia page. It is a T-class brown dwarf, which means it glows magenta in color and shows spectra for methane. Rimward of that, and 9 parsecs south, we come to HD 4628, a star that should be more loved than its name implies. It is a solitary example of the coveted K-class dwarf stars, with 70% the Sun's mass and fully a quarter its luminosity, and much lower surface activity, meaning it is less likely even than our own Sun to flare. All this together suggests it may be older than the Sun, at 5.4 billion years. Frankly, I'm astounded astrobiologists aren't drooling over it. Stepping outside the bounds a little and jumping 9 parsecs back north, we come to Gliese 445, fairly typical red dwarf about the size of Proxima Centauri, which in about 40,000 years will have an interesting double encounter with humanity. First, Voyager 1, the farthest man-made object in the universe, will pass within 1.9 light-years of it. Then, it will briefly outpace Proxima Centauri to become the closest star to the Sun, at just 3.45 light-years. For a future meet-cute with the human race, it isn't dolling itself up. No planets have been found around it to date. Following the boundary eastward and jumping 7 parsecs south, we come to this brown dwarf. It also has a Wikipedia page, but with good reason. Its mass is just 12.7 Jupiter masses, which places it a hair's breadth below the 13 Jupiter mass limit for brown dwarfhood, which means it isn't technically a brown dwarf, but a free-floating planet. If so, how did it form? Was it ejected from another star system, or did it form like a star from gravitational collapse? If it did, where does the boundary between planet and star lie? Will we ever know for certain? Evidence suggests it is a vibrant planet, for one so lonely. Variability in the light observed across its surface has been interpreted as constantly shifting cloud patterns, while radio emissions are believed to be aurorae, similar to those which exist on Jupiter. Next up, and 9 parsecs north, we come to this brown dwarf, which I almost Google-whacked myself on. Chord of that, and 2 parsecs farther north, we come to Gliese 1151, a red dwarf of Proxima-ish dimensions whose luminosity, metallicity, etc. suggest it is about 2.5 billion years old. In 2020, radio emissions from the star suggested its magnetic field may be interacting with an Earth-sized planet in a tight 1 to 5 day orbit. Don't get too excited, though. Wikipedia compares the likely relationship to that of Io and Jupiter, only scaled up. Jupiter's magnetic field completely ionizes every molecule in Io's scant atmosphere, effectively transforming it into a planet-sized microwave. Imagine such a world with Venus's atmosphere, and we have a new definition of hell. Next to it, but 10 parsecs south, we come to TZ Arietis, another Proxima-ish red dwarf, but with 2 confirmed planets, one about twice the size of Neptune, the other approaching the mass of Saturn, and both outside the habitable zone. Eastward of that, and 1 parsec north, we come to one of my favorite stars, Teegarden star. Teegarden star is fascinating for many reasons, not least because it was found without a telescope. Bonnard J. Teegarden's main claim to fame isn't hunting stars, but tracking potentially hazardous asteroids for NASA. In 2003, after compiling 8 years' worth of near-Earth asteroid tracking data, Teegarden realized that it might be possible to mine it to search for previously unknown stars. And, sure enough, once the images were scanned, this star emerged from the depths. It was, unsurprisingly, dim, even dimmer than Wolf 359, and at just 84 Jupiter masses, only just above the 75 Jupiter mass threshold to qualify as a star instead of a brown dwarf. An actual fusing star so close to Earth had not been found in decades, and that feat alone gained the star its discoverer's name. But that isn't what makes Teegarden interesting today. In 2019, radial velocity measurements detected two Earth-sized planets in close orbits around Teegarden's star. The first, Teegarden B, has an orbital period of just 5 days. The second, Teegarden C, orbits the star in just 11 days. Think of the generations of science fiction writers who never conceived a trip to the planet Teegarden. Nonetheless, both are apparently outside Teegarden's razor-thin habitable zone. B is too close. In our system, it would lie between Earth and Venus, while C is in a position similar to Mars, though with a higher CO2 content than Earth's in its atmosphere, it might still be habitable. Additionally, again and again I have had to mention flares as a block to habitability, but Teegarden appears to be fairly quiescent, particularly for a red dwarf. While I doubt you'd want to take your kids to Teegarden, it may yet be a paradise to someone. 5 parsecs north, we arrive at Groombridge 1618, one of 3 stars named for Stephen Groombridge, a name I still have to check myself before trying to pronounce. An orange dwarf star, it has about 2/3 the Sun's mass, about 60% its radius, but just 15% its luminosity. Its habitable zone lies roughly between the orbits of Mercury and Venus. Again, it tends to act more like a red dwarf, being pocked with star spots and the occasional flare. Studies from orbital observatories have hinted at a planetary system, including a highly reflective debris disk at 51 AU, and, more tantalizingly, a possible planet of 4 Jupiter masses just within the star's habitable zone. Unfortunately, follow-up searches have failed to relocate it. Another 5 parsecs north, we arrive at Groombridge 1830. Also known as Argelander's star, Groombridge 1830 is a slightly anomalous yellow dwarf star of about 2/3 the Sun's mass and radius. Despite being a G-class star like the Sun, it has only 20% the Sun's luminosity. This is due to its relatively low metallicity, which decreases its opacity and thus the pressure on its escaping light, which causes it to lose energy more efficiently than other solar-type stars. Its low metallicity is due to it being a halo star, like Barnard's star. Halo stars are the regurgitated remains of past galactic mergers, and so are almost always older than stars in the galactic disk, in which collapsing nebulae produce a steady stream of new stars. Groombridge 1830 is estimated to be about 500 million years older than the Sun, which under normal circumstances would be a phenomenal case for a developed biosphere. Unfortunately, much like the smaller stars it appears to be emulating, Groombridge frequently emits superflares, a la Proxima Centauri. Flares 10 to 100 times more powerful than those produced by the Sun. No planets have been found around it as of yet. Let's hope they have a lot more ozone than we do. Next to that, and 4 parsecs south, we come to Gliese 412, a binary of 2 red dwarfs, one about half the size of the Sun, the other about 10% its size. The two are separated by over 100 AU, leaving lots of room for planets, but again, as of yet, none have been found around either. 4 parsecs back north, we find Gliese 450, a red dwarf about which I can find no information whatsoever. East and slightly rimward, and 1 parsec north, thus placing it near the edge of the sphere, we find the G-class Sun-like star 61 Ursae Majoris. It is a near twin to the Sun, with about 90% its mass and radius, and about 60% its luminosity, similar to Tau Ceti. Even its metallicity is similar, though detailed examination suggests it's about half the Sun's age. Unlike Tau Ceti, it appears to have no debris disk, although it also appears to possess no planetary companions, at least of Jupiter size. Jumping over Gliese 84, a red dwarf binary about which I can find no information, we arrive at the map's first quintenary, Alula Australis, which surprisingly is not part of the Sydney Mardi Gras, but the first multiple star system ever discovered, identified as a binary by none other than William Herschel in 1780. The dominant pair have an orbital period of about 60 years, and a separation of around 10 AU. A bit cozy for planets, but not impossible. B's closeness to A apparently allows their magnetic fields to mingle, creating herds of star spots across B's surface. Each of the pair is also a pair in itself, though their companions are too close to be directly imaged. They have been indirectly detected using spectroscopy. They are both likely red dwarfs, though if B's companion is a red dwarf, it is likely so dim it makes Teegarden's star look feisty. Finally, in 2012, a fifth component, a brown dwarf named that, was found to orbit the system at a distance of 4,000 AU. According to star names, their lore and meaning, the name Al-Kafsa Alula comes from the Arabic word meaning the first spring, as in the spring of the gazelle, rather than the season. To the naked eye, the star appears to form a double with the star Alula Borealis, which Arabic astronomers called the second spring. Seemingly next door to Alula, but actually 7 parsecs south, is DX Cancri, a very dim red dwarf, dimmer even than Teegarden's star, though it is listed in several 20th century star catalogues, so it has clearly had little problem being noticed. Forward of that, we get to Ran, or as I've been calling it for my entire life, Epsilon Eridani. The name Ran was chosen as part of an IAU poll in 2015, in honor of the Norse goddess of the ocean. A name I can say I prefer, particularly now that I know I was supposed to be pronouncing it Epsilon Eridani all these years. It is odd, though, given that it is a naked-eye star, that it took so long to get a name. I mean, that's how it works. Ptolemy gives a star a long and ponderous Greek description. It gets translated into Arabic. Then an Italian monk garbles it up, and we get a name. But somehow, like with Alpha Centauri, despite following that exact path, it never happened. At first glance, Epsilon Eridani does not appear particularly interesting. It's a solitary orange K-type star, about 3/4 the size of the Sun, and about 80% its mass. But inside, it's raging. Its magnetic field is 40 times stronger than the Sun's. Its corona is twice as hot, and its solar wind is 30 times stronger. The heliosphere generated by that monster solar wind extends outward to 8,000 AU, 70 times the size of the Sun's heliosphere. At any one time, you can expect a tenth of Epsilon Eridani's surface to be covered in sunspots. That makes it possible to track its rotation, which is just 11 days, twice the speed of the Sun. All this indicates that Epsilon Eridani is a very young star, perhaps between 200 and 800 million years old. This may damper the giddy optimism of yesterdecades, which saw Epsilon Eridani targeted for the first SETI searches, but it makes it fascinating for entirely different reasons. The stream of discoveries that has emerged from this system since the 1980s has all but confirmed one overriding fact. Epsilon Eridani is a solar system in formation. For astronomers, this is a candy store. To be able to study the motions and ructions of planetary genesis in a star system so close to Earth has been a gift that keeps on giving. In 1983, the famous, or perhaps infamous, infrared satellite IRAS detected an infrared excess around Epsilon Eridani, showing that it was surrounded by a dust disk. Observations by the James Clerk Maxwell Radio Telescope on Mauna Kea show that the dust disk extended from 30 to 100 AU, peaking at 60 AU. This makes the disk a younger analog to our solar system's Kuiper belt. In order to still be extant over the age of Epsilon Eridani, the belt must have been created by collisions between 11 Earth masses of cometary objects, similar to the 10 Earth masses believed to have originated the Kuiper belt. Clumps within the belt have suggested the existence of a planet in a 3-2 resonance, but that remains unconfirmed. The Spitzer Space Telescope has detected at least 2 asteroid belts within the Epsilon Eridani system, one in a similar location to our own asteroid belt, the other, denser belt, lying between the inner belt and the dust disk. There is speculation that the belts could only be held in place by the presence of 2 as yet unconfirmed planets. There is one reasonably confirmed planet in the Epsilon Eridani system. though it is probably the most controversial detection to be placed on this map. Now officially named Aegir after the husband of Ran, the planet, which some still argue doesn't exist, is about the size of Jupiter and has a semi-major axis of 3.4 AU, which would place it at the outer edge of our asteroid belt. Aegir was detected by astrometry, historically not the most reliable method, and by radial velocity, an uncertain method for Epsilon Eridani, given that its extreme activity can mask any radial velocity signals. Also, because the Spitzer infrared telescope detected an asteroid belt at 3 AU, some argue that if Aegir existed, it would have disrupted that belt eons ago. Given that its insane solar wind would likely sterilize any nascent planets, even if they had finished being pummeled by storms of giant meteors, Epsilon Eridani is an unlikely candidate for an Earth-like planet. On top of that, if Aegir exists, it likely would have knocked any planets in the star's habitable zone out of orbit. But then, it's not Epsilon Eridani's job to live up to our expectations. It's just a baby, for God's sake. East of Epsilon Eridani and 11 parsecs north, we get to Ross 905. Also known as Gliese 436, Ross 905 is a red dwarf about 40% the size of the Sun, with just a 40th its luminosity. Since its metallicity is less than half that of the Sun, astronomers estimate that it is very old, possibly as old as 10 billion years. So far, so Barnard's star. What's really interesting about Ross 905 is the planet orbiting it, confirmed in 2007 when it was revealed to be transiting its star's disk. Transits are great for exoplanet studies because when combined with radial velocity measurements, they allow you to measure both a planet's mass and its radius, which gives you its density. Its mass was found to be just 21 Earth masses, while its radius was just 4.3 times Earth's, comparable to Neptune. Like Neptune, it is believed to comprise a rocky core enveloped by a mantle of superdense ices and an outer atmosphere of hydrogen and helium. Very much unlike Neptune, however, the planet orbits its star at a ridiculous 1/36th of an astronomical unit, completing an orbit in just 2.6 days. Ross 905b was the first of this new class of objects, dubbed hot Neptunes, to be discovered. In the decade and a half since its discovery, hot Neptunes have proven so difficult to find that exoplanet hunters speak of a hot Neptune desert. The favorite hypothesis for the desert's existence is that Neptune-sized objects so close to their stars would have their dense atmospheres blown away by the intense solar wind. In 2015, this was confirmed to be the case for Ross 905's planet, as Spitzer found it trailing a tail of gas 14 million kilometers long. Only problem? Ross 905 is supposedly ancient, which means that the planet should have been reduced to a rock ages ago. Unless, of course, it began life much larger. Some have speculated that Ross 905b may be the first known example of a helium planet, a gas giant whose hydrogen has been boiled off by proximity to its star. But perhaps the oddest thing about 905b is that its orbit appears to be perpendicular to its star's equator, suggesting its journey to its current location was not a smooth one, and may have involved other planets. East of Ross 905, we find the map playing a little trick. While the star system appears to be a binary, it is in fact two separate stars aligned with one another, but separated by 2 parsecs, Ross 104 and Gliese 388. Ross 104 is your standard red dwarf, but Gliese 388, also known as AD Leonis, has the distinction of being one of the most active red dwarfs known. At any one time, 3/4 of its surface is magnetically active, often generating coronal loops up to a third as large as the star itself. The corona is double the temperature of the Sun's corona. All this might be because, unusually for a red dwarf, Gliese 388/AD Leonis is very young, just 200 million years old. Rimward of Gliese 388, and in line with the Sun, we finally arrive at the first star in this survey with an ancient proper name. I'll admit, as was noted in the comments to the last video, I have been pronouncing that name Procyon, which is incorrect. It was a lame attempt at ancient Greek purism, and a failure, as a true Greek purist would have pronounced it Prokwon, from the Greek pro kwon, before the dog. I asked myself, if that name had been an animal genus, would I have pronounced it Procyon? And the answer is yes, I would have. So I will bow to consensus this one time and call the star Procyon. Procyon is one of the relatively few Greek stellar names to have survived the muddle of history intact. It derives from the fact that the star always rises in the sky before Sirius, aka the dog star. Together, the two stars and their constellations, Canis Minor and Canis Major, were often viewed as the hunting dogs of Orion, perhaps helping him slay the great bull. One particularly sad Greek tale depicts the star as Myra, the dog of Icarius. Not to be confused with Icarus, Icarius was the lucky mortal to whom Dionysius chose to pass on the art of winemaking. When Icarius tested his first attempt on some local shepherds, they soon shared with Noah the ignoble mythic fate of being the first people ever to get pass-out drunk. Deciding Icarius had poisoned them, they killed him. His loyal dog then ran to his daughter and dragged her to his corpse, whereupon they both took their own lives. A very Greek story, if I may say so. Procyon, while merely an F-class star, one rung above the Sun, and outmassing it by just 1.5 times, is exceptionally bright, 7 times the Sun's luminosity, when F-type stars generally max out at 5 solar luminosities, which leads astronomers to assume that it is a subgiant, a main sequence star just beginning its journey into red gianthood and eventual death. If our descendants last about another 100 million years, they will see Procyon as a great red orb in the sky, like Aldebaran, but far brighter. As was noted in the 19th century, Procyon is not one star, but two, as it is orbited by a white dwarf called Procyon b. The star was initially only inferred from Procyon's motion through the sky, and even today is hard to image due to the extreme difference in apparent magnitude. White dwarfs in close orbits around other stars are surprisingly common. Indeed, an entire class of supernovae, type 1a supernovae, occur because white dwarfs draw too close to their primaries, pulling their matter toward themselves until they reach critical mass and explode. This will not happen to Procyon, as its stars orbit at a safe distance of 15 AU, completing an orbit every 40 years. It is estimated that Procyon b's progenitor had about 2.5 times the mass of the Sun, and ended its life about 1.2 billion years ago. Just 1.2 light-years rimward of Procyon, we find Luyten's star. I'll be honest, I have no idea why this star is called Luyten's star. I mean, yes, Willem Luyten did determine its proper motion, just as he did for 30,000 other stars. Is it the closest of his stars to Earth? No, that's Luyten 7268. Is the star particularly notable? Well, yes, but not for anything known when it was named. It's a medium-sized red dwarf about a quarter the size of the Sun. Its relatively slow rotation and low metallicity suggest it is quite old, perhaps as old as 8 billion years or more. Other than that, I have no idea. A friend I contacted, bless his altruistic soul, spent hours searching the Astrophysics Data Service to dig up references to the name, and could not find any before the year 2000. Still, I don't begrudge Luyten the name, and in recent years the star has become famous for other reasons. In March 2017, radial velocity revealed two fairly typical planets in orbit around Luyten's star. The first, an Earth-mass planet, the second a super-Earth of about 3 Earth masses. What made this super-Earth atypical, however, was that it lies in its star's habitable zone, making it one of the best candidates for extrasolar life found to date. As an added bonus, Luyten's star is unusually calm for a red dwarf, showing little of the violence typical of its younger colleagues. Life has not only had a chance to form on Luyten b, but to thrive and evolve. In 2018, Sonar, an arts festival in Barcelona, beamed several specially composed musical pieces, including one by electronica pioneer Jean-Michel Jarre, toward Luyten b. Assuming no faster-than-light communication, we should receive a reply no earlier than 2043. West and slightly rimward of Luyten's star, we come to 40 Eridani, also known as Omicron 2 Eridani or KEED, 40 Eridani is a trinary system comprising a K-type orange dwarf star of about 80% the Sun's mass and radius, orbited every 8,000 years by a binary of a red dwarf and a white dwarf, which in turn orbit each other at about Pluto's distance. The white dwarf, 40 Eridani c, was the first of its kind ever identified. Also, for once it negates the issues with its red dwarf partner being a flare star, as any life in its system would have been wiped out of existence when it became a white dwarf. 40 Eridani a, however, could very easily host a habitable planet. And while we don't know if it hosts a habitable planet as of yet, we do know it hosts a planet. 40 Eridani AB was discovered in 2018, and is a super-Earth of roughly 8.5 Earth masses. With an orbital period of just 42 days, it is far too close to be habitable. I have particular reasons to hope for a habitable planet around 40 Eridani, because, according to Gene Roddenberry himself, 40 Eridani A is the sun of the planet Vulcan. If there was ever a time we needed to make contact with a supremely logical civilization, it would be now. Coreward of 40 Eridani, we arrive at LTT 1445, a trinary system comprising 3 red dwarfs. B and C orbit each other once every 36 years, and together orbit A once every 250 years at roughly Pluto's distance. In June 2019, TESS, the Transiting Exoplanet Survey Satellite, NASA's successor to Kepler, found a super-Earth of around 8 Earth masses in a close 5-day orbit around B, which bodes well for A. Coreward of LTT we get to... I seem to have gone round in a circle. Let's see, what's the nearest star? Oh, right. I think I'll stop here. Well, that was a jaunt and a half. Longer than the first video, and we still have only done half the stars in the second ring. I have no idea how big the next video is going to be. Depends on how much information I can dig up on Sirius, which is going to be a lot. Thank you to everybody for all your lovely comments about this video series, and let me know if you'd like it to continue beyond the third video. If you're new to my channel, please like, comment, and subscribe. Stay curious, fellow seekers.